Example 2.2.3, draw a phasor diagram for the circuit presented in the following figure. And I've added a little condition where X sub L is greater than X sub C. The value of the inductive reactance here is larger than the capacitive reactance there. So to start drawing this figure, and I'm going to bypass the givens and the required for this one. There just really isn't anything to do there. But to draw a phasor diagram, we got to first start with an axis here, and we have one axis that represents resistance or the real part of an impedance, and then we've got another part that represents reactance or the imaginary part of an impedance, and then they will represent the real part of a voltage, that'll represent the imaginary part of a voltage, etc. Right? Another way to think of this is 0 degrees and 90 degrees. And you can extrapolate that around the axis. So to start with, we need to pick a reference for the phasor diagram. Typically, we will take the source voltage to be that reference. So we want to start by drawing that reference phasor. I'm going to draw it in yellow because that's what color, maybe this gold color here, because that's what color the phasor, the voltage source is colored in here. Since it's the reference, I'm just going to draw it pointing in the positive real axis. So that pointing in the positive real axis, really what I'm drawing there is that the voltage has angle of 0 associated with it. So that's that yellow arrow there. So now what we want to know is kind of what is the nature of the whole current in there flowing in here. So in the condition that X sub L is greater than X sub C, we know that this guy is going to dominate that. That means the current associated with this current draw right here, I, is got to be, it's going to be, the nature of the circuit's inductive, and so we know that the current in an inductive circuit lags the voltage. So we know current, if you remember from the reading, Eli is for inductive circuits, so current lags the voltage. That means the current flowing in this circuit is going to have a negative angle associated with it. How big? I don't know because I don't have any numbers here. I just know that it's going to be an inductive current. So like current's purple here, so let me pick a purple color. So I'm going to draw that current there in the fourth quadrant, and so that's I right there. And I know that it's in the fourth quadrant because it's got to lag the current or the voltage phasor. So that's the phasors for the reference and for the circuit current. So I still have to draw these three right here. To draw these three, I'm going to use the current to figure out what their angles are. So I'm going to go to this red resistor here, and I know that voltage and current in a resistor are in phase. So that means that the angle of the current vector has to be the same as the angle of the voltage vector or phasor across the resistor. So that means I can't really say anything right now about their magnitudes, but the that's going to be VR. It's going to point in the same direction as I because voltage and current in a resistor are in phase. Now let's move around the circuit to the inductor here. I know that voltage and current in an inductor are 90 degrees out of phase. I know that the voltage leads the current by 90 degrees in a purely inductive circuit. So we're looking at just this little guy here. He's a purely inductive circuit. His current is I. His voltage needs to be 90 degrees out of phase with that. So I'm drawing this green. It's a little wiggly. That's just because my hand's not very steady on this computer. That should be a straight line. Computer's lagging a little bit too. So anyway, that's the best representation I can give you for the inductive voltage VL. I guess I'll add the fact that that's equal to I times X sub L. And I guess I could have indicated that this was equal to I times R. Okay, finally I want to finish with a blue guy here, and it's going to be that I want to draw the current and voltage relationship relationship across that capacitor. I know that I here is the current through that capacitor since everything's in series. That means that I need the equivalent of this. This is ICE current leads voltage in a capacitor right here. And we know in a purely capacitive circuit like this little part is right here, there's a 90 degrees phase shift, so there needs to be 90 degrees between the current and the associated capacitor voltage. And I's got a lead V, so that means there needs to be a 90-degree angle this way. I'm going to draw V sub L, or sorry, V sub C smaller than V sub L because I know that X sub L was larger than X sub C, so this vector needs to be larger than that vector here, and that value is going to be I times X sub C. So mathematically you can see that this one has to be larger than that if X sub L is larger than X sub C. We also see that the vectors for V sub L and V sub C in a series circuit point completely in opposite directions. They are 180 degrees out of phase with one another. Their current through those devices is the same, therefore their voltages have to be 180 degrees out of phase.